Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA which looks at the cement industry's response to climate change around the world and other topics of interest. I'm Ian Riley, CEO of WCA, and your host on the Clinker Factor. Today, I'm talking to Apoorv Sinha, founder and CEO of Carbon Upcycling Technologies. Apoorv was recently recognized with the prestigious Top 35 Under 35 award from the Canadian Clean 50 organization for his groundbreaking work in carbon utilization. Apoorv, welcome. Perhaps we could start with you giving us a short introduction of yourself and how you came to set up Carbon Upcycling.
Hi, Ian. Thanks for having me. Great to be a part of the podcast. I've heard a few of your episodes and obviously I've known you for a period of time now. I began working at Carbon Upcycling when we founded in 2014, primarily looking at ways of mineralizing carbon emissions into solid products. We're a Canadian company headquartered in Calgary, but now have operations in Europe as well as in the US. But at the time, really our main focus was carbon-based nanomaterial production. We weren't really looking at cement or cementitious materials at the time. So it's been quite an evolution over the last 8.5 years or so to get to where we are. But, I'm a chemical engineer by training, and it's definitely kept a lot of that chemistry piece of my education in play. And I've enjoyed learning a lot about both the challenges as well as the opportunities that the building material industry generally has to face over the next 10 years or so.
So you've scaled the business from starting with lab scale, I guess a few grams, up to your pilot scale that you've got now. What have been the biggest challenges that you've encountered during that time?
Yeah, they've really been kind of different stages of evolution. I'm also a young dad, so I think about, the different stages of parenting as well as just a parallel. But yeah, I think at the early stage, Ian, I would say from 2014 all the way up to probably 2018, a huge amount of our work was engaging with a lot of research partners. So universities that had characterization data, that had expertise in specific areas such as polymer chemistry or nanomaterial characterization or cement chemistry increasingly as we got towards 2018 or 19. And I would say at the time, the challenges weren't really related to many of the things that we consider challenges now. At the time, it was a much more open-ended kind of research project, as you might do. You had a very forgiving and nice supervisor for a PhD. You had a bit of money. You weren't constricted to look at only one angle because you had funding to kind of look at whatever you wanted. And as long as you could make a compelling enough case, you could look at it. So I would say as we went from, a cookie jar reactor that was doing, as you mentioned, 2 to 3 grams at a time, dealing with local machine shops and pressure vessel shops and stuff to get that done was relatively straightforward compared to some of the complexities now of trying to work with large multinational companies and looking at deploying things, with their operating teams in different regions of the world. However, it was exciting in the sense that for the first 4.5 years of Carbon Upcycling's kind of existence, we weren't really sure about where the product market fit was for the tech. It was almost like a solution looking for a problem to solve. And one of the big north kind of stars for us was where can we get sequestration potential of CO2 that really makes a meaningful difference? And primarily for carbon-based materials, we were able to get some incredibly exciting numbers. I mean, we were seeing that we could sequester 100 kilograms of CO2, 100 to 250 kilograms of CO2 per ton of carbon that we process. So what I mean by that is not carbon from the CO2 gas, but carbon as in like graphitic carbon or amorphous coal, which we could activate to actually get carbon to sequester CO2. And this was quite interesting. What we ended up finding was, most of these applications were very niche and just not large volume enough to really make millions or hundreds of millions or gigatons of impact. And so the scale-up piece, I think, became really real for us as we competed in the Carbon X Prize competition. We did that starting in 2018, where we got into the semifinals with a few other companies that you've hosted on your podcast, and essentially realized that, there is, if we can keep the costs low and come up with a scheme that isn't overly intensive from a capital standpoint, there is an opportunity in the building material space, and specifically around supplementary cementitious materials, which, as you know, has become kind of the core focus of the company in the last 3 or 4 years.
So maybe you could introduce the technology and how it works so that our listeners can get a basic understanding of what we're talking about here.
Absolutely. Yeah. So from day one, I think we were kind of hesitant to get into wet carbonation in its normal form. So if you look at literature across the board, most of the focus has been on aqueous carbonation, any materials that have, high pH. So obviously in the case of cement, like we talk about anything that has calcium oxides or calcium silicates that we can look to carbonate. And generally, I would say by and large, the heavy majority of approaches involve wetting the material, injecting CO2 in and putting it into some kind of an autoclave or some kind of a curing chamber. Our premise when we started in October 2014, at least at the lab scale, was to look at how can we carbonate or add CO2 to graphite to make single layer graphene. One of the things about all carbon chemistry is you want to keep it away from water. Like the only solvents that you can really use are oil-based or water-repelling solvents, which tend to be very expensive. And our whole kind of premise that we got a little bit of money from the provincial government in Alberta, Canada for was a dry, low energy process to make nanomaterials that could go into, a range of applications. And in true kind of North American startup mode, we kind of oversold without having, a bunch of evidence to prove that we could make what we thought we could make. But I think to our credit as an organization, we were able to make single layer graphene oxide that we continue to test for a couple of really neat applications, like in 3D printed plastics and a couple of polymer applications that could even have some medicinal kind of applications. But by and large, I guess to answer your question about the core tech, the idea was how do you take a powder and chemically activate it while you're breaking it down? So you're starting with something that's a few hundred microns. Most of the graphite that we started with was, about 10 times the size of a cement particle. So 300 to 600 microns. And we would grind it down in the presence of the right chemistry so that it would actually absorb CO2. And what we found was that it would actually functionally change how the graphite / few layer graphene interacted with within a composite or in a certain use application. And so really what we've done in the last 4 years is translated that understanding of carbon-based nanomaterials and getting them to sequester or chemically absorb CO2 to cementitious materials or materials that are calcium and magnesium rich, or at least have some considerable components of that, and use that in those materials. And primarily what we found is that because many of these industrial byproducts or even some of these natural minerals that we've tested, because they have so many impurities, the only way that we could get this ready for, an industry that is willing to live with that kind of stuff is basically the building materials industry. And so it was in 2018 that we started pivoting towards that. And in the last, I would say 2.5 years, we built a pretty solid portfolio of about 14 patents to really cover how this works for different families of materials, ranging from industrial glass waste to slags to fly ash, which has been a core focus of ours, being where we are in the world. And yeah, I think overall it's been a great learning curve, and there's a lot more that we still need to do for sure, but it's been a steady start so far.
So if I could summarize that, then you've identified a range of materials, including traditional SCMs like GGBS and fly ash, but also including materials that are not used as SCMs or not usually used as SCMs like waste glass, steel slag, clays, various other things. And by treating these with a mixture of mechanical activation and CO2, sequestration of CO2, you're able to activate the materials so they make more effective SCMs. Is that a rough summary?
Yeah, much more succinct in my summary, but yeah, exactly right.
So you have a couple of commercial projects that you're working on now. I mean, what can you tell us about those?
Yeah, it's been quite exciting, Ian, because I would say it was about 2.5 years ago that we really began to understand the latter part of what you mentioned, which is not looking at the staple SCMs that are already around, but rather at alternative materials which currently have issues for adoption in the space. And so that includes materials like off-spec ashes, steel slags that are currently not able to be used as they are, as well as, certain natural pozzolans and volcanic ashes as well. And so really what's been quite gratifying is, we were funded almost entirely by a couple of angels and Canadian government kind of support for the majority of our life. It was about 2 years ago that we started to look at the venture capital route and really started to explore the product market fit. And with the two most engaged partners, namely Cemex and CRH, we've been able to identify two specific plant locations, one in the UK, one in Eastern Canada, where we have gone away from our core work on fly ash, which was kind of our major technical focus till about 2 years ago. And in one case, we're looking at an industrial waste glass, and in the other case, we're looking at a type of slag from the steel industry. And in both of these cases, again, going back to what we just discussed about the technology, really what has resonated with them is that this is a dry, semi-dry process that can be integrated right at the cement plant instead of needing to be, scaled down for a ready mix or a precast plant downstream. And so the fact that they can plumb the CO2 directly into our system, it can sit right by their kilns, has been a key factor of attraction, I think, for what we've proposed. And in each case, really the premise is that when you're a multinational cement company with, different supply chains in every different location, a solution, quite, I think, ironically, to scale needs to be able to really work at the micro scale, because you're not going to be able to get the same feedstock in every location. And so if you cannot build in some level of optionality, and it does not have to be, radical in the sense that, you don't have to take whatever is available, but you need to have some level of, I guess, choice. And really our intent over the next year and a half with the Series A fundraise that we just finished earlier this summer is to use the resources that we now have and the team that we're building to demonstrate that we can take these two family of materials and create a cementitious product that they can put right into their finishing mill or send the SCM directly to a ready mix site that might be able to do the blending. And if we can show that, and we can show that we can do 20-30% clinker factor reduction with our SCM, really our thinking is that could open up a range of options and allow these companies to be very competitive with price as you mentioned, materials like fly ash and GGBS become less and less available, and as a result become more pricey and costly to attain.
Yeah, so I think this is a couple of very good points that you raised there. Well, one, of course, is the point of additionality, and a lot of contractors in the UK, when they talk about low carbon concrete, they're really thinking about using slag. And of course, the slag is already used in Europe. So it's a case of if one contractor uses more slag, another one is using less slag. So it's not really helping the overall global position. And of course, there are certain applications that require slag for its low curing heat properties, and we really ought to be using the slag for that. So I think the additionality and the fact that you can apply your technology to other materials is really important. And the other thing, though, that you also brought out there is the fact that the materials may be different in different places. And we see with, for example, some of the work that's being done on geopolymer concretes that companies and technologies are being developed to use different materials in different places. Often these are mine tailings or old stockpiles of slag and fly ash and so forth. So there's, I think, a greater interest in using local materials, which obviously help reduce logistics costs and the carbon associated with that. So I think in bringing those two issues together, that's a very interesting contribution that you're making to the overall mix of solutions that we have. Can you give a little bit of an idea in terms of how much carbon reduction your technology is able to deliver? So I think you've got one portion of it, which is the direct sequestration into the materials, and then another portion of it, which is the replacement of cement in the concrete mix. So can you sort of quantify that for us and explain how that works?
Absolutely. So talking about the sequestration piece first, Ian, as you'd appreciate, really that's as much a function of the process as it is the chemistry, but ultimately the ingredients that you're served with, in whatever constituents of feedstock you're exploring are principally the most important factor in how much CO2 you can sequester. So a huge amount of our work within the Western Canadian frame has been with Class F fly ash, which is in Europe called the silicious fly ash. It's silica rich with free lime or calcium oxide content, at least as per XRF characterization, of less than 6%. In many cases, like in Alberta, it's less than 4%. So what ends up happening there is that no matter how efficient you are with your carbonation process, wet or dry, you're only able to get up to about 20, 30, 40% of that. So meaning, on a per ton basis, if you hit 10 or 15 kilos of CO2 sequestered per ton, that's actually not that bad. That's almost, 30, 40% of the theoretical maximum. And when you take into account all the other things that are fighting you, like the different heavy metals that get in the way of that of the kinetics of that carbonation, etc., or the crystal structure, which is not really much of an issue with fly ash, but can be an issue with slags as an example, it can all get in the way. So, that would be an extreme example on the low end of 1%, 10%, or 1 to 1.5%, sorry, of uptake that you might be able to get. On the higher end of the spectrum, you'd have materials like slags or, bypass dust or kiln dust, where you can easily get 100 to 250 kilos of CO2 sequestered per ton. And so, obviously we have some work we can't really talk about that we're doing with one of your groups, but there are some interesting angles there around actually getting a direct sequestration number, which is material. Because, if you're in the 1 to 2% range, it really doesn't change much. There was an announcement we saw by one of the big admixture companies in Europe recently where they were taking concrete fines and I think getting about 15 or 20 kilos of CO2 per ton of final product. And it's an interesting statement because, as marginal as it sounds, I do have to commend them to say that, like, we know through the 4 years of work we've done that is still not straightforward. I mean, 2% sounds like a very low number, and it is, admittedly, objectively. But given the constraints that you have, we know how hard we had to work with slags as an example to get that number from 3-4% at the beginning to the 14-15% or 140 to 150 kilos per ton that we can do now. Like it did not come easily. But to your point, that is one element of our carbon abatement / kind of the whole carbon life cycle story. The second element is the abatement, which is the direct substitution of that clinker that we're able to achieve by increasing the reactivity of the final product. And, whether it be Class F fly ash or even, a couple of slags that we've tested, we've been able to show that we can do a 20% displacement of the clinker. So, we've done baseline tests with OPC, we've done it with GUL cement or PLC cement, and in each case, been able to show at least a 20% substitution without compromising on the 7-day and the 28-day strength of that material. In the case of fly ash, we've been able to do multiple rounds of long-term durability testing as well. And no surprise to someone like you who's been in the field, but for people watching that might not understand, but the more clinker you reduce generally tends to have a better impact on durability and resilience as well. And so expectedly, we saw our RCP numbers generally improve. So the rapid chloride permeability, the rebar protection work, as well as some of the other durability factors that play into climate adaptation and resilience. And so overall, I would say even for materials that have high CO2 sequestration potential, like let's say for a slag, what we generally find is that the abatement or the clinker substitution element tends to be 4 times bigger as a factor on a life cycle basis compared to the sequestration component. So even if we sequester 150 kilos of CO2 into the slag, when that slag replaces the clinker by 20% in your ton of cement, that 20% displacement is 4 times more valuable in your LCA than the 100 kilos of CO2 that went in. And ultimately that boils down to just, the math of how concrete, how much cement is in the concrete and the high embodied carbon footprint of making clinker. And so, yeah, it's fairly complicated. And that number for a high uptake material like slag would be 4 to 1. In the case of a low uptake material like a silicious fly ash would be 5 to 1. So it really, even though the sequestration numbers are, 10 kilos versus 150 kilos, the overall life cycle analysis of the carbon footprint, if you were to adopt our technology, would only tweak, or move 20% between the two materials, which we found to be quite insightful. And ultimately, again, just talks about how much inherent emission is just built into making clinker and why that's so valuable with any new material you put in.
What have you found in terms of the impact of particle size on performance? Is there something that you can do on the particle size of different materials that has a big impact on the cementitious performance of the end product?
Yeah, it's an excellent question. And obviously we've been now grinding materials for 9 years, and we still learn a lot every time, we talk to folks that have been doing it for way longer than us. I think Generally speaking, what I would say is it is material specific. By and large, the expectation, quite rightly, is that the smaller your particle size, the better your reactivity. With many materials that can have trade-offs as well. And again, this is not across the board, but for many materials, if you grind finer, the workability and the water demand can become an issue. And so, it's hard to draw general rules, but what I would say as kind of two maybe high-level statements is number one, the type of grinding really matters. Not all grinding is the same. So you could get to the same particle size with two different grinding techniques, but if your surface area, your morphology, your characterization of amorphous versus crystalline content, if these things are not exactly identical, which they'll never be for two different mills, I mean, at least to our limited knowledge so far, that can make a big difference. And so it's not just the size, it's also the type of, particulate that you make at the end. And the second thing I would say is that by and large, it also depends on the mode in which the material actually supports cementitious reactivity. So in our case, one of the, I guess, more technical pieces, I suppose, is that even though we're carbonating the material, let's say if you were to compare us against a company that creates carbonate-based cements, right? And I won't name any, but obviously you and I know a few. But if you're making carbonate-based kind of strength, if your strength in that final product is coming from carbonates, you'll sequester more CO2 because you're trying to drive the carbonation. The more carbonation you drive, the stronger your material. And, that can potentially come with other drawbacks like those, it creates its own set of kind of contexts. In our case, we carbonate the material and then still have the material participate in hydration chemistry like normal cement. And what that really means is that's why it allows for that compatibility where, this can be used as an SCM as opposed to an alternative cement. And, one way to look at it would be to say, well, this is not disruptive enough. Like if you really want to change cement, make it all new carbonates and stuff, right? Like completely change the paradigm of how we make cement. And I guess to an extent, we're kind of more boring than that. And we're trying to look at how do we just stick to the hydration chemistry and improve it with a material that has already become a carbon sink. And I would say that the reason I'm saying all of this, and I apologize for being so long-winded in all my answers, but I would say that if you have a material that's only helping because of fine particle size, it's probably not contributing to hydration much to begin with. It's probably just doing a kind of a nucleating effect and a filler effect. And, of course, with very fine limestone and very fine silica and stuff, like people see that. And so that could happen. With those materials, there's no doubt the more particle size reduction, the better. If you have a material that then hydrates, and does it hydrate like a slag, like a GDPS, or does it hydrate like an alkali-rich material like Portland cement? Again, size can either help or hurt, and it becomes more nuanced. But I would say definitely for inert materials or materials that have very low reactivity to begin with, just because of their chemistry, size helps a lot.
Okay. So if we look forward to the next few years, I mean, how do you see carbon upcycling developing over the next 2 or 3 years?
I would say, Ian, I guess at a philosophical level, the mission that Carbon Upcycling has is to be the most impactful carbon tech company of this decade. And by that, obviously there's a bunch of that we can internalize, but we understand that there are going to be externalities. And if, one of the big premises of our work is there are other companies looking at slags. There are some of them that are looking at slags in, much further downstream than us. There are some that are looking upstream, like looking at adopting that into the meal for, what you feed into a kiln. We're looking at the wedge where you can fundamentally decouple the production of a cementitious material from using fossil fuels or needing high temperatures. Our thinking is, yes, there will be more technologies over time to electrically make heat and things like that, and that will happen. But our view overall is that unless you get away from the need to have things bake at 1400 degrees C, it is going to be fundamentally a challenge for the over 3,000 cement plants in the world to really, really decarbonize. And so our premise of mechanochemically activating materials and decoupling production of cementitious materials from calcination is a big premise of ours. And our thinking is that for a couple of these families of materials, we definitely want to help our partners, both the ones now and hopefully more in the future, to start taking this route and work with us so that it's a win-win. Overall, if our impact comes because by 5 years from now, people start adopting this methodology generally and start changing how they do these things, we still consider that to be impact that was catalyzed by us. And so I would say, generally speaking, if we can make that decoupling happen, and I think to the point that you made earlier, really drive home that value prop of like taking someone else's waste to make, a good feedstock. that chemically and performance-wise can work for cement. That's really, really important because so far, from everything we hear, since the 80s, when SCMs really began to get used in mainstream construction, there hasn't really been a time like now where, people are worried about paying more for GGBS than they've paid for cement, or paying more for fly ash than they paid for cement. And so, when you couple that with the fact that we not only are shutting down the things that make these materials, like, blast furnaces are becoming more scrutinized, coal power plants are shutting down. And so that's creating a squeeze right at the wrong time for when we need these SCMs the most. And so if we can somehow, facilitate the adoption of these other waste materials to lower that and still allow for clinker substitution to happen meaningfully, to us, to whatever impact we can play in driving that and speeding that up would be a massive win.
So one of the material families that must be interesting are clays. And of course, we know that calcination of clays can make quite effective cementitious materials, but you've also been looking at mechanical activation, and obviously mechanical activation has a number of advantages in terms of energy, in terms of carbon footprint, and indeed in terms of permitting when you look at permitting new plants. Is that an area that you see a lot of potential in?
Yeah, this might be one of the few answers where I'm quite cagey and don't give you a long answer, but yes, the short answer is absolutely see a lot of potential. And yeah, I think it's an area that we're definitely quite focused on in our R&D efforts.
Okay, well, excellent. I think that's a really interesting area for the future, and maybe a good point for us to bring the conversation to a close. So, Apoorv, thanks so much for talking to me today. It's been a pleasure.
Likewise, Ian. As always, great to talk to you again.
Thanks for listening to the Clinker Factor podcast today. If you've enjoyed it, do subscribe, and please recommend us to friends and colleagues and anyone else who you think would be interested in what's happening in the cement and concrete industry around the world. WCA is a not-for-profit company. Please visit our website to see the services that we offer